In this example, you want to give the electron and molecular geometry for 3 different compounds. So in order to do this, there are a variety of steps in order to get to the ability to answer these questions. The first step is to draw the Lewis dot structures for all of these. Well, the first step is to calculate your valence electrons. So we have 5 plus 3 times 1 plus 7 minus 1, which is going to be 14. So you lost 1 due to a positive charged ion as opposed to gaining 1 for a negatively charged ion. In this case, we'll create a Lewis dot structure where we connect all atoms to the central atom, creating octet for the remaining electrons. So we have 8, 10, 12, 14. We've used all of our electrons. We know that there is a positive charge. We need to calculate the formal charges. So for the nitrogen, it's going to be 5 minus 1/2 of all of the bonding electrons, which is going to give you plus 1. We now have a positive charge on our nitrogen. So the first step is to create a Lewis dot structure. The next step is to draw a VSEPR structure of this in order to determine the electron and molecular geometries. In this case, with a steric number of 4, we know that it should look something like this. It doesn't matter where we put all of these because all of these are going to be symmetric. Both the electron and the molecular geometries for these are tetrahedral. Here's a typo. It should say electron, not election. Okay, so those are both the same. So now for our next atom, we can calculate our valence electrons. So 6 plus 7 times 4 is 34. All right, so sulfur is going to be our central atom. So we have a Lewis dot structure where we look like this. Turns out when we fill octet for all of the fluorines, we've used 32 of our 34 valence electrons. The last 2 will end up on the central atom. We now have a steric number of 5, which means that our base geometry is going to be a trigonal bipyramidal. Okay, now we need to draw a VSEPR structure to determine what the molecular geometry is. So, sulfur is our central atom. We know that these 4 need to be somewhat oriented to one another, but the question is, where do we put the lone pair? If we know that the base geometry looks something like this, the fluorines and the lone pairs can't just go all over the place. It turns out for the electrons to consume the maximum amount of space, we will put them on the equatorial plane, and we will put the fluorines on the axial and the remaining equatorial planes. Don't forget to add your lone pairs. And from here, this molecular geometry is actually going to be seesaw. Because if you don't observe this, this looks like a seesaw, okay? For our next element, or for our next compound, we have a PF6 minus, so we need to calculate our valence electrons. 5 plus 6 times 7 plus 1 for the negative charge is 48. We'll connect our phosphorus to the center. 1, 2, 3, 4, 5, 6. So we'll add our fluorine atoms. Fulfill, all of the octet for the surroundings on our Lewis dot structure. Okay, from here we've used 8 on all 6. We have actually used all 46 of our electrons. So we know that the base geometry is, or the Lewis dot structure will look like this. Turns out that when we have a steric number of 6 or 6 things connected to the phosphorus, that is going to be octahedral. And so this, an octahedral structure, the base geometry looks like this. Since all of our substituents are the same, we can put them wherever we'd like, making sure to include all of our lone pair electrons. All of these fluorines are 90 degrees from one another in an octahedral arrangement. And this molecule is symmetrical. So in order to determine both the molecular and the electron geometry, we start with the Lewis dot structure, determine the number of steric centers, aka how many things are connected to our central atom. We would draw the base geometry. Then we can determine the molecular geometry after that.